In this video, we're going to talk about how to find the area between two curves. Okay, so here, this is important for many applications. Okay, so we've already looked at how to find the area under or between a curve and the x-axis. So now we're going to look, well, what if it's bounded by a curve on both sides? Okay, so that's a little bit more general from the method before. Okay, so suppose we wish to find the area between f of x and g of x from a to b. Okay, so between x equals a and x equals b. So we're looking for this area in the middle of the two graphs here. Okay, up until x equals a and x equals b. Okay, now because I've drawn these so that they're both above the x-axis, so I can convince you, hopefully quite easily, that the area that we're looking for is going to be the area between f of x, the bigger one, and the x-axis. Okay, so that's all of this. So this blue area. Okay, so that's going to give me more area. I definitely got everything, but I got even more. So then what I'm going to do is I'm going to subtract this green area under the g of x, or the smaller graph. Okay, so if I subtract all of the area underneath the g graph, so that's all the area that I didn't actually want, then I should get the area in between them. Okay, so when you have one that's bigger than the other for the entire interval, then the area between them is the area under f of x. Okay, so this was the blue area in the picture. Okay, subtracted by the green area. So that's the definite integral from a to b of g of x dx. Okay, so that is the green area. Okay, now using the properties of the definite integral, I can actually write this as a single definite integral. So f of x minus g of x. Okay, so that, and this is actually going to work no matter if they're both above the x-axis or not. It's just easier to see when they're above the x-axis, but it actually works no matter what. But we're going to talk about that in a minute. So here's the actual theorem. So if f and g are continuous functions, f is bigger than or equal to g on the entire interval, then the area between the two curves and between x equals a and x equals b is going to be the definite integral from a to b of the bigger function f of x minus the smaller function g of x. Okay, now I'm just going to write here, so this is the bigger one, okay, on the interval, okay, and g of x is the smaller one. So it's always the bigger one minus the smaller one. Okay, so let's do an example. So if I want the area bounded between the graph f of x is negative x squared plus 1 and the graph g of x, which is 2x plus 4, between x equals negative 1 and x equals 2. So one thing we can do is graph these two functions. Okay, so g of x is a line, so it has y-intercept at 4 and then a slope of positive 2. Okay, so it's going to be the line that looks like that. Okay, so this is g of x. Okay, and then f of x is a parabola that opens down that's been shifted 1 up. Okay, so it's going to look like that. Okay, so now having drawn the graphs, we can see which one is bigger. So negative 1 to 2. Okay, so we're looking at so we want that area there. I'm just going to highlight it in yellow here. Okay, now it does go a little bit below. So f of x is a little bit below the x-axis. Okay, so here we can see from the graph that g of x is bigger than f of x on the entire -1 to 2 interval. Okay, so we don't need to do what I'm going to do right now, but if we couldn't graph them, then we might want to know where, so without the graph, what we'd want to do is find the intersection points, okay, which these ones don't have any, okay, and we're going to see how we can see that. Because that's where it could switch from one being bigger than the other. So those are the points we're going to use. So this, what you do is you set the functions equal to each other. Okay, so I'm going to have -x squared plus 1 is equal to 2x plus 4. Okay, and then I want to solve for x. I'm going to move everything to the right-hand side. So it's going to be x squared plus 2x plus 3. This doesn't factor nicely. So if we use the quadratic formula, this means that x is -2 plus or minus 2 squared minus 4 times 1 times 3 over 2 times 1. This is -2 plus or minus the square root. Now it's 4 minus 12, so that's going to be -8 over 2. Okay, and clearly this square root of a negative number doesn't exist. So f of x does not equal g of x for any x. Okay, this tells us that one graph is always higher than the other. Okay, so finding one point, just comparing one x value is enough. Okay, so if I look at f of 0, okay, so at x equals 0, the y value for f is f of 0, which is -0 squared plus 1, so that's a 1. Whereas g of 0 is 2 times 0 plus 4, which is 4. So we can see that f of 0 is smaller than g of 0. So this is another way, okay, so since f of 0 is less than g of 0, and 1 is always bigger than the other, this means that f of x is always less than g of x. Okay, so for all x, and in particular on our interval. Okay, now like I said though, since we had the graph, we didn't actually need to do any of that. Okay, so the graph was enough to see this. Okay, but either way, so we know that our area is going to be the integral from -1 to 2 of our bigger graph g of x minus our smaller graph f of x with respect to x. Okay, so g of x is the 2x plus 4 graph, and then I want to subtract the minus x squared plus 1 graph. Oh, and I'm running out of room here. I should be more cautious. So in fact, I'm going to move that up because I think I need more room than I have. Okay, so then if I simplify, this is going to be x squared plus 2x plus 3. Okay, so now I can take the antiderivative, so that's 1/3 x cubed plus x squared plus 3x, and I want to evaluate from -1 to 2. So I take that whole thing and I plug in 2 everywhere, so it's 1/3 2 cubed plus 2 squared plus 3 times 2, and then I subtract the whole thing with -1 plugged in, so 1/3 minus 1 cubed plus -1 squared plus 3 times -1. So this is 8 over 3 plus 4 plus 6. 1/3 times negative 1 to the 3, that's going to be negative 1/3. So this is actually going to be plus 1/3 minus 1 plus 3. And if you simplify all of that, you should get 15. Okay, now I just wanted to mention here that this little bit here would count as negative area if we were just thinking about f of x. Okay, but here, since we subtract the area of f, it actually gets added as a positive. Okay, so if you think about what you're doing for these two, okay, it's going to be all of this, so that's the area under G, and then when I do F, I'm going to be subtracting that part, which is good, because that's going to get rid of it, but then I'm also going to subtract this part, but it's actually a negative number in the definite integral, so it's going to be added in. Okay, so it does work even though f of x goes underneath the x-axis. Okay, so like I mentioned earlier, it's not necessary to graph the functions. Okay, you can just look for the intersection points and then test each interval. So I'm just going to outline again. So to find intersection points, we set the two equations equal to each other and solve for the x values. Okay, any x values that do that. And then we use these x values, okay, of the intersection points to break up the interval. Okay, so this is from A to B, okay, where we want to compute the area. And then we want to test a point in each one to see which function is higher. So unlike when we're just talking about one function in the x-axis, we're always looking for where does the function cross the x-axis and where is it above and where is it below. Here, I don't actually care about the x-axis, but I do care about when the functions cross each other. And then I want to know which one is on top. So when they cross, and we're going to do an example of this later, when they cross, that's when you're going to have to break up your integral. Okay, so I wanted to briefly talk about why it doesn't matter that they're underneath if they go below the x-axis. So if you think about this function, these two functions here, so the area that's stuck between them, okay, is going to be this area here. So I'm going to call this A1. Okay, so let's say that this is f of x, okay, and this one is g of x. Then this one is g of x plus 3, and this one is f of x plus 3. And we can see that all I've done is shift it up by 3. So the area should be the same. So I'm going to call this A2, okay, but they should be the same area. Because all you've done is taken this exact thing and moved it up. So you haven't stretched it or compressed it or any way. So the area in between them should be the same. So it might be easier to see in this picture that if I go under G, I'm going to get all of this area. And then if I subtract the bit that's under F, I'm going to get rid of all the stuff I don't want. Okay, so it's easy to see maybe that A2, and I'm just going to say, so they nicely meet at -2 here, but over here it's not a nice point. So let's just call it B. So A2 is going to be the integral from A to B, but now my higher function is g of x plus 3, and my lower function is f of x plus 3. Okay, but notice what happens if I simplify this. the 3's cancel out. And so I get g of x minus f of x. Okay, and that is exactly how the formula tells us to compute A1. Okay, so you can see that they would be the same area. So that's why it doesn't matter. You don't have to worry about the x-axis anymore. Okay, let's try another one here. So here I'm going to not graph them right away. So let's look for intersection points. So it's between the curves y equals e to the x plus 1 and y equals 1 minus x. Okay, between 0 and 3. Okay, so we want to find intersection points. Okay, so I'm going to set them equal to each other. Okay, now if I subtract 1 on both sides, the 1's actually both go away, and I get e to the x equals negative x. Okay, this equation is actually difficult to solve. Okay, but we don't actually need to solve it. Okay, so any chance, so in order for e to the x to equal negative x, we need negative x to be positive, since e to the x we know is positive. Okay, so that means that we need x to be negative. Okay, now that's enough to say that there's no intersection points on our interval, which is 0 to 3, because those are x's that are positive. Okay, but it would have to be a negative x. So we're going to have no intersection points. So now I know that one of them is always bigger. So let's test x equals 1. That's in our interval. Okay, so e to the 1 plus 1 is approximately 3.7182. Okay, and 1 minus 1 is 0. Okay, so the e is bigger. Okay, so that means e to the x plus 1 is going to be bigger than 1 minus x on the interval from 0 to 3. Okay, so our area is going to be the definite integral from 0 to 3, e to the x plus 1 minus 1 minus x. Okay, and then if I simplify this, the 1's are going to cancel out, and I get e to the x plus x. Now if I take the antiderivative of e to the x is e to the x, and of x is 1/2 x squared. And I want to evaluate from 0 to 3. So I plug in 3 everywhere. So that's e to the 3, oops, plus 1/2 3 squared minus e to the 0 plus 1/2 0 squared. So this is e to the 3 plus 9 over 2. And then minus, now you might be tempted to say this is 0. Okay, but e to the 0 is a 1. Okay, the 0 squared is definitely 0, but this is a 1. So my area is e cubed plus 7 over 2, which is actually I'm going to just move down a bit here. Plus 7 over 2, which is approximately 23.586. Okay, so that's our area. Okay, and if you wanted to see the picture of what's happening, okay, e to the x plus 1 is the graph of e to the x shifted up 1. So it's going to have a horizontal asymptote. And look like that. Okay, horizontal asymptote at y equals 1. And then the graph of 1 minus x goes through, has a y-intercept at 1, and then an x-intercept also at 1, so a slope of -1. Okay, so it looks like this. And you can see that there is an intersection point, but it's going to be not in our interval. Okay, so we wanted to go from 0 to 3, which, okay, this is going to be too high. So the area we're looking for, okay, it's stuck like that, and it comes up here all the way down to there. Okay, and then in between. Okay, this does meet. I should have drawn it a bit better, but okay, so it does cross that line. So but so that's our area, and it is approximately 23.586. Okay, so I want to just do one more, and that's where the curves switch. Okay, so here we need to worry because there's more than one. There is an intersection point in our interval. Okay, so we're going f of x is x squared minus 2x, g of x is x, and we're on the interval from 0 to 4. Okay, so we find the intersection points. So I set the two things equal. So x squared minus 2x equals x. So that means x squared minus 3x is 0, which is x times x minus 3 being 0, which gives x equals 0 and x equals 3. Okay, they're both in the interval. So I want to break up my interval, so from 0 to 4, and I'm going to break it up at 3. Okay, so it could switch which one is bigger. So now I want to test a point. Okay, so f of 1 is 1 squared minus 2 times 1, so that's negative 1. And f of 3.5 is 3.5 squared minus 2 times 3.5, which is 5.25. Okay, and then g of 1 is 1, and g of 3.5 is just 3.5. So you can see from 0 to 3 that g of x is bigger than f of x. Okay, here's where they're equal at 3. And then on the other side, f of x is bigger than g of x. Okay, so because of that swap, we need to do the area in two separate definite integrals. So we're going to go from 0 to 3, and then we're going to put g of x first. And then we're going to add from 3 to 4, and here we put f of x first. So now we just want to compute those. So in here I'm going to have 3x minus x squared. And then this one, it's just going to be the reverse, so it's going to be x squared minus 3x. So the antiderivative here is 3 over 2x squared minus 1/3 x cubed, and then plus over and then evaluated, sorry, from 0 to 3. And then here I have 1/3 x cubed minus 3 over 2x squared, and I evaluate from 3 to 4. So I take this whole thing and I plug in 3. So 3 over 2 times 3 squared minus 1/3 times 3 cubed. And then I take the whole thing and I plug in 0. Now all of these are going to be 0, so I'm just going to put 0 there instead of writing that all out. Okay, so that is the first one. Okay, and then the second one, I put in the 4, so 1/3 4 cubed minus 3 over 2 4 squared minus putting in 3. So 1/3 3 cubed minus 3 over 2 3 squared. And that is the answer for the second definite integral. So now I'm just going to expand everything out. So this is 27 over 2 minus 9. Okay, the 0 goes away. And then I have plus 64 over 3 minus 24 minus 9 plus 27 over 2. And if you simplify all of that, you should get 19 over 3, which is approximately 6.33. Okay, again, I'm going to draw the picture just so we can get an idea of what this looks like. Okay, but like I said, we did all of it without needing it. So the f of x has so 0 and 2. So it's a parabola. Okay, that looks kind of like that. Okay, and then g of x is just the line y equals x. Okay, now this point here where they meet is at 3. Okay, this is at 2. And we want it to go to 4. So the area that we just calculated is under there, so in this region here. Okay, and then also this little bit over here. So that's what we calculated. Now all of these examples gave you an interval. Okay, so all these ones that I happened to pick said which interval they wanted. Okay, if it just says find the area of the region enclosed by these two equations. So for this one, you would do exactly the same thing. Okay, but for this one, you'd want the area enclosed. So it would just be between these two intersections. So this area is stuck in between them. So that's what they would be looking for there. Okay, in the extra example video, there will be examples that are stated like that. So that's how we can compute area between curves.